Um, Welcome to solving session for linear algebra. I am Siddhi Balu Ambore, a PhD student at IIT Gandhinagar. So today we will solve a few problems related to the syllabus covered in the week 1. So let us start with first question. So whatever we will solve in this live session or problem solving session are problems which will be more or less related to what you will have in your assignments, but they won't be exactly similar to what you have to solve in the assignment. Okay, so let us start with the first problem. So for first problem, we have this status that let V be a set, and it is again set of real numbers, and we define following operations on V. Okay, so my handwriting is visible to all of you, right? It is not that small. You can read it. Okay, I assume that it's okay. So we define addition on this V to be for U comma V in V. We define U plus V to be U minus V, and scalar multiplication where scalars are coming from real numbers. So let A be a scalar from real numbers, and if U is in V, then we define U into V to be A into U to be A square U. Note that this addition and this multiplication here are usual subtraction and multiplication in real numbers. Okay, so this is usual multiplication in real number, and this is usual subtraction in real number. Okay, so our first question is this V under addition defined above is closed or not? Okay, or is V closed under addition defined above? So can somebody guess? So this is interactive session, and it would be great if you can unmute or write your answers or guess in the chat. So close under addition, I hope you know the definition. So close under addition means, so the addition defined here, that is U plus V. So if we have U and V in V, then we need to check whether this U plus V, this V addition is our vector addition defined here, belongs to our V or not. Okay, we need to check that. So what is this U plus V? But so it is U minus V. And we know the set of real numbers is closed under subtraction. Like when we subtract two real numbers, we again get real number. So this addition on this vector space, or not the vector space, the addition on this set V is closed. Okay. So answer to this question will be yes. The addition defined on V is closed operation. And if you have any doubt, feel free to unmute and ask anytime. Okay. If you have any problem, and if you are not aware of any concept which we are using in the problem, feel free to unmute and ask. Yeah. So this was our first question. And let us see, let us go to second question. That is, we closed under scalar multiplication. I mean the scalar multiplication which we have defined above. So what does this mean? What we need to check that if A is in R, I mean our scalars are coming from the real numbers, and if U is an element of set V, then whether AU belongs to V or not. This is what we need to check. Okay. But what is A dot U? It is A square U, right? As per our definition here. So A dot U is A square U. A square into U in real numbers. So this we know belongs to R because multiplication is closed operation in R. So that's why again this scalar multiplication which we have defined on V is closed. Okay. So far so good. I mean, any doubts? Okay. Hmm. So let us move to our next question. If you do not want to unmute and ask the question, you can always write the question in the chat. I am here, I will read the question and answer your question. So question 3 is again related to the above set V and the operation we defined. So we would like to check which of the properties set V satisfy with the addition and scalar multiplication defined as above. Okay, so we would like to check. So there were 8 properties given for a set to be a vector space or not. So we would like to check whether those properties are satisfied by this V under the addition and the scalar multiplication we just defined earlier. Okay, so we will start with the property 1. So what is property 1? Anyone know? Okay, so property 1 was related to commutativity. Okay, commutativity means the operation addition which we have defined on set V is commutative or not. Commutative means that whether commutativity means we want to check whether U plus V is equal to V plus U for U and V from our set V or not. Okay. So what is U plus V? So as per our definition of addition, U plus V is U minus V, right? And what is V plus U? It is V minus U. Exactly. So it is V minus U, as you said. So we know that. So if this property to satisfy, I mean this star to satisfy, that in that case we must have U minus V is equal to V minus U for all U comma V in V. But not that this V is R, right? So we know that in this V minus U is actually in real numbers, the normal subtraction operation in real numbers, it is minus of U minus V. And if we take U not equal to V, that in that case, this U minus V is not equal to minus of U minus V, right? So that means that this addition which we have defined here is not commutative. I mean, the addition defined on V is not commutative. Okay. Any problem like what is happening, or is it confusing because of what is addition, what is subtraction, or anybody who is not able to follow, please feel free to ask anytime. Okay, I will give you a second to just go through. If you do have any doubt, you can just ask me. Okay, so we will check our property 2. Okay, so property 2, if you know, it was associativity. Okay, so associativity. So we want to check whether for U, V, and W from V, U plus V plus W, whether it is equal to U plus V plus W. Okay, so let us write what is U plus V plus W is. So what is this? U plus, what is this addition? This is vector addition, which we have defined on V. Okay, so it is V minus W. It will be V minus W. We have taken V first and then, okay. And then it is then subtracting this. So this is now a real number. I mean element of V. So we have to check that this U minus V minus W. Okay, so this is U minus V plus W. And now note that when we are at this stage, this is not normal, but usual subtraction in R. Okay, and this is now usual addition in R, and it is no more our vector addition which we have defined earlier. And now, so this is our first, I mean, left hand side. Now we will write what is our right hand side. So U plus V plus W. So we will first clear the bracket using first addition. So it is U minus V plus W. And then it will be U minus V minus W, and which is U minus V minus W. And again, at this stage, this is usual subtraction in R. And we have to see whether these two are equal. I mean, U minus V plus W, whether it is equal to U minus V minus W or not. Okay. And if you see, I mean, if we take any U is equal to V is equal to W, then in that case, what this will be? U minus U plus U, which is equal to U minus U plus or minus U, not minus U. So this will be what? U is equal to minus U. But we know that if U is non-zero, in that case U is not equal to minus U, right? So that's why again the associativity is not satisfied. Any doubts? I hope there is no doubt, or if you have, please unmute and ask. Okay. So now we will check whether this satisfy our property 5. So property 5 of wait, okay, let me take this. Property 5 was existence of multiplicative identity. Okay, so our so this is related to scalar multiplication and how it was defined. So I will write the definition of scalar multiplication again, that if we are taking u in R and a in R and u in our set V, then a dot u we are defining it to be a square u. Okay, so we want to check whether there exists one of V in V such that 1V into u is equal to u for all u in V. Okay, so that is we want to find this element 1 or multiplicative identity of our vector space or not vector space but our set V, which satisfy this property, that existence of multiplicative identity. Any guess which number from V? So note that our V is set of real numbers. Okay, which V can satisfy this property or which V satisfies this property. Exactly. So as Hitvi said, one would always satisfy, right? Because this 1 into u is what? 1 square u, and which is again 1 into u and u in real numbers, right? This u is a real number. So that's why the existence, I mean, we just need to have existence of this multiplicative identity at this moment. We are not asking for its uniqueness. But since we are already here, can somebody guess what other element which is satisfies this property, that multiplying that element to u will again give me the same element under this operation? Okay, I mean, in our case, the way we have defined our multiplication, note that even if I take -1 here, -1 into u will be -1 square u, and now this is real number addition multiplication, and this is again giving me u. Okay, so in our case there are more than one element which is again giving me the same element when I multiply that element by u. Okay, if it is confusing for you, just leave, but yeah, the existence is satisfied, and by by element 1 in V. Oh, sorry, 1 in R. 1 is in R, which is our set from which scalars are coming from. Okay. Any doubt? The existence is satisfied. We have an element which satisfies this property. Now we would like to check property 7. So property 7 was distributivity. So distributivity means whether the scalar multiplication is distributive or not over addition. Okay, so that is given a in R and u comma v in V, our set V, then we want to check whether A into u plus V is AU plus AV or not. Okay. So let us write our LHS, which is A of u plus V, which is what? A of u minus V. Now this is multiplication in real numbers, so which we know that it is AU minus AV. And what is our RHS? It is AU plus AV. But this is what? AU minus AV, right? This is in our V, this is in our V. And this subtraction we are doing in V. Okay. So in this case, this LHS is equal to RHS. So our condition is satisfied. So the scalar multiplication is distributive over addition defined in V. And now the last property which we would like to check is whether a scalar multiplication is linear or not. The multiplication we have defined is linear or not. That's what we would like to check. Yes. Property A, whether scalar multiplication is linear. That is, if A comma B belongs to R, I mean A and B are scalars, and if V is an element in V, then we would like to check whether A plus BV is equal to AV plus BV or not. Okay, so what is our LHS in this case? It is A plus B into V. And this is multiplication in our vectors, in our vector set V. Okay, so what is this? It is A plus B square V. Okay, this is our scalar multiplication. So this is how it is defined. And now once we have this expression, we are in real numbers. So now we are in real numbers and we are multiplying these elements A, B and V as a real numbers. Okay, so this is our LHS, and what we have in RHS is AV plus BV. So now note that this scalar multiplication here is in V, this is also in V, and this addition is also in V. Okay, so how it is? It is A square V plus B square V. And still this addition is in V. And now I'm doing our vector addition as we have defined in V. So it will be A square V minus B square V. Okay. However, in this case, it will be again this simple A square plus AB 2AB plus B square. Okay, and we can clearly see that if we choose A and B properly, we can see that this is not true, right? So in particular, if I take A to be 1 and B to be 2, in that case, my LHS, if we check, it will be 1 plus 2 will be 3 square. So it will be 9V in this case. I mean, if we take just these examples, and in here it will be 4V minus 1V minus 4V, which will be 3V. Okay. So these two are not equal. We can see here I am getting 9V and here I am getting 3V. In fact, minus 3V. Okay. So this scalar multiplication is not linear under the addition which we have defined on a vector set of vectors V, and also the scalar multiplication the way we have defined. Any doubt how this, it is 9v and this is minus 3v, or anywhere it is confusing that where is the addition occurring in vector space and where the addition is occurring in um, real numbers? Any doubt, please ask. Because now we are over with our first question. We just wanted to check whether the addition and scalar multiplication defined here on V, whether those satisfy the properties of vector space over R as not. And we see that this addition and scalar multiplication are closed under addition and scalar multiplication. However, they do not satisfy the a few properties of uh, vector space. For example, they do not satisfy the commutativity. It does not satisfy the associativity. It has a multiplicative identity, and it is also distributive. But again, the scalar multiplication is not linear. Okay, so this set V, the set of real numbers, the way we have defined addition and the scalar multiplication here, is not a vector space. Okay, so far any doubt? If not, then I will move to next question. So I don't know which question number this was, but okay, question number 4, let's write. So we would like to see for A in M3R. So M3R is set of all 3 cross 3 matrices with entries from real numbers. Okay. Do we need to check identity? And yes, we can check. If you want to check, we can see that. Can you guess what whether the multiplicative inverse or identity satisfy here or not? Yes, Bharat. Do you have any question? Or Bharat? Any question? Okay, okay. So yes, I just went through a few properties of scalar multiplication. I mean the vector addition and scalar multiplication which we have defined on V. But yes, we only checked 5 properties. There are total 8 properties of for a set to be vector space over a base field. And you can check the rest properties. And if you have any doubt, feel free to raise those doubts or raise those questions in the Google Classroom or discussion group which we have. Okay. Any doubt from the lectures and any doubt from the this live session which are happening, you can post your questions there. Okay. For now, we understand that there are few properties which we does not satisfy. So it is not a vector space. And yes, you can check the identity and inverse property. And if you find, if you face any doubt there, feel free to ask those in the Google Classroom. And for now, we will move ahead to next question. I hope that is fine. Okay, so let us go to our next question, and then we have this. So again, for this question, we are working on matrices, 3 cross 3 matrices over R, and this TRA will be called is called as trace of A, and it is sum of all diagonal entries of A. So if I write A to be A11, A12, A13, A21, A31, A22, A23, A32, and A33, then or in shorthand I will be writing it like this from 1 to 3. Okay, this will be the shorthand which I will be using from now on, and then in that case this trace of A will be just A11 plus A22 plus A33. Okay, these elements, this addition of these elements is trace. Okay, and further we have this determinant of A. We all know determinant of A, and further, and A power t, I mean not power t but A raised to t, this symbol represents the transpose of matrix A. Any doubt for the symbols we will be using here? Okay, so these are the setups which we will have, and we want to check that we will be looking at whether the W's, which I will define in a few minutes, are vector subspaces of this say, M3R. I mean the set of all matrices of order 3 are vector subspaces or not. Okay, so which of the following are vector are subspaces of M3R? Okay, so our first is we define W to be A in M3R such that trace of A is 0. Okay, so what is this? This is set of all. If I write A to be A I J I comma J from 1 to 3 in M3R, my condition is that addition of A11, A22 plus A33 needs to be 0. We want to check whether this is vector space, vector subspace of M3R or not. So what is your guess? Is it vector subspace or not? Just a guess. So first of all, to check any subset. So what is subspace? So first let us understand that. So we say that a W subset of vector space V. So V is now vector space. We say that W is subspace or vector subspace of V if W is closed under addition and W is closed under scalar multiplication. Okay, so meaning yes. Since 0 is in trace A, okay, it is subspace. So Arijit's guess is that it is a vector subspace of V. So yes, so we will prove it formally, that we will check that it is closed under addition and closed under scalar multiplication. Okay, so let us start with it. So what we have is, so what is closed under addition means, we did that in our first question, that if we take two elements from W, now we are working on W. So we want to check the closure, I mean the whether the operation is closed on W. So our elements will be from W and we want to check whether those elements land again in W or not. Okay. So let A comma B in W, and we want to check what we want to check, that A plus B belongs to W or not. Okay. So A and B belongs to W means what? Trace of A is 0 and trace of B is 0, right? So as I said that A, then what is now? And I want to check for this element A plus B, right? So what is A plus B, this element? Can somebody tell me what this is? So if I write A to be Aij from 1 to 3, Bij, I comma j from 1 to 3, then what this A plus B is? We are adding those, yes, trace of A plus trace of B is trace of A plus trace of B. Okay, so that is what will happen here. Okay, and it comes from this property, that not property, but the way we define the addition of two matrices. Okay, from 1 to. So as who Arijit said, yes, corresponding elements will be added for the addition of two matrices, and as that's what Hetvi said, and Arijit said that trace of A plus B uh, is equal to trace of A plus trace of B. Okay, but even if you do not know this property, we can understand from here that from the definition of trace, the way we have, the trace of A plus B here will be A11 plus B11 plus A22 plus B22 plus A33 B33. And since this is basic addition in set of real numbers, we can, it is commutative and associative, so we can shuffle the elements and we get A11 plus A22 plus A33 plus B11 plus B22 plus B33. And this we know is 0 and 0, right? Because trace A and B are from W and we are taking trace. So trace of A and trace of B is 0 here. Okay. So using this, we get that this A11, A22, which is again, it is nothing but, let me write, trace of A, trace of B. Trace of A plus trace of B, which is 0 plus 0 and 0. Okay. So our W is closed under addition. Okay. So even if you do not know this property, which is really really handy when we are doing immediate calculations. So please understand this. And further, we want to check whether it is closed under scalar multiplication or not. So how we are defining scalar multiplication here? So it will again be the multiplication of the scalar to each component. So if I say A is Aij, I comma j from 1 to 3, then if I take C in R, then CA is, we are multiplying by C to each entry of A, and then we will do our further work. Okay, so then now what will be the trace of CA? We want to check whether CA is in W or not. Okay, so trace of CA is what? CA11, CA22 plus CA33. So it is what? C of A11, A22 plus A33. Okay, so it will be, again, since A we are taking from W, this implies that trace of A is 0. This is for scalar multiplication, or let me write full scalar multiplication. C into 0, which is 0. Okay, one new message. Yes, C into trace of A is 0. Yes, so, and trace of A was 0, so it will be 0. So again, this is closed under scalar multiplication as well. So the two conditions which we need to check for W to be subspace are now satisfied. Okay, any doubt? Any doubt? Uh, Okay, so W is a subspace because it satisfies both scalar multiplication and vector addition here. Okay, I wrote 0, which belongs to, so this implies, let me write it clearly, which is 0. And since trace A plus B is 0, implies A plus B belongs to W. So we also have addition is closed under W. So W is subspace of V. Okay, any doubt? No, right? If you have anything, please feel free to ask in chat or unmute yourself and ask. And now we do this for another subset of V, our M3R again. So we take A in M3R such that trace of A is now 1. And what is your guess whether this will be subspace or not of V? So V is again our M3R. Okay. So first we will do for addition. So as Arijit had said that trace of A plus B was trace of A plus trace of B. So if we take A comma B in W, then trace of A will be 1 and trace of B will be 1. But then in that case, trace of A plus B using this property is what? Trace of A plus trace of B, which is 1 plus 1. But now it is 2, right? So what can we say from this? Is A plus B belongs to W? Exactly. It's not a subspace because A plus B doesn't belongs to W. Because what is W? W is all the vectors, all the matrices with the trace to be 1. We want trace to be 1. So if A plus B, if we wanted it to be in W, then it must have a trace to be 1. But we got that trace of A plus B is now 2. So this W is not a subspace of M3R. And even before going to the subspace condition, um, we can also check as Hetvi in the previous question. I mean the previous where we were checking that. I mean not Hetvi. Yeah, Arjit had said that 0 is in trace A. I mean the trace of 0 was 0, so his guess was it is a vector subspace. So we can do that also here. I mean the 0 of addition, I mean the additive identity of this space M3R is a 0 matrix and trace of which is 0, and in that case this 0 itself, the additive identity 0, doesn't belongs to W. Okay. So this anyway is not a vector subspace. Okay, so that is also a good catch that we first check whether additive identity belongs to W or not, and we can clearly say that it is not a subspace of set V. Third vector space which we would like to check is all the A in M3R such that trace of A transpose is now 0. Can somebody quickly tell me that what to be done or what is the catch here that we can directly say that this is a vector space or a subspace of M3R? We already has carried out the work already for this set. Can somebody tell me? Okay, so the first observation which we need here is that trace of A transpose is actually trace of A.
Yeah.
Yes, yes. As Arijit said, we already know for A it's subspace and we just transposing it. Exactly. So trace of A transpose is again trace of A. And so what this becomes is trace of A to be 0. This set again become trace of A to be 0, which is again what we did in our question, or not question one, the first subspace for which we checked. So it is a subspace. Okay. This thing again, if you don't know, please get used to this. Okay. So fourth one, A in M3R such that A plus A transpose is 0. So what is your guess? A plus A transpose we need to be 0. First, check whether 0 belongs to this set or not. Does 0 belong to this set? This 0 means the 0 of matrix. Yes. 0 belongs to W, right? Because 0 transpose is again 0. Or, yeah, 0 transpose is again 0. So 0 plus 0 transpose is 0 plus 0, which is 0. And it belongs to W. So our first condition is satisfied. I mean, not the first condition, but our quick check to have W to be subspace or not is done. So now we want to check addition is closed or not in W. Okay. So let A comma B to be in W. So what does that mean? A plus A transpose is 0 and B plus B transpose is 0. Now we want to check what? Whether A plus B belongs to W or not. Okay. So what is A plus B transpose? Can somebody tell me what is A plus B transpose? Yes, it is B transpose plus A transpose or A transpose plus B transpose, one and the same thing in here, because um our addition in matrices is commutative. Okay. So this is what we have. Then A plus B transpose, A plus B. Now we want to check whether this A plus B transpose was for A plus B to be in W, it must satisfy this condition. So now we are doing what? A plus B plus A plus B transpose, which we know that A plus B plus A transpose plus B transpose, which is what? So now addition is commutative and associative. Since M3R is a vector space, we can happily do this and we will get this. And what is this? This is 0 and this is 0. So 0. So what we get here, that A plus B is in W. Okay, so our addition is satisfied. And now scalar multiplication. So let C in R. Then what is C into A? And let A be in W. So CA is what? C. So let us start with, we want to check what CA transpose plus CA is what? Okay. So what is CA transpose? It is just C into A transpose. Okay. Plus C into A. And what is this? C into A transpose plus A, or doesn't matter, but let me be. On. Yes. It will be C into 0 and this is 0. So note that here just I'm being clear here that C dot A means C. If I write it is C I J I comma J from 1 to 3, then it is C A I J I comma J from 1 to 3. Okay. So we are component wise multiplying each element of A by C. Okay. And you can easily check this thing which I used, that CA transpose is C into A transpose. Okay. And since this is 0, using this we get that CA is in W, and again the scalar multiplication is satisfied here. Any doubt? So this is clear, right? So this is again a vector space. Now the final, the final vector space which we would like to check for M3R is, let W to be A in M3R such that determinant of A is 0. So what is your guess here? Is this a vector space? I mean the vector subspace of M3R or not? Okay, it is vector subspace. Are you sure? Okay. Okay. So how can we? Okay. So let us start with the basic thing. Our first thing to check is addition. So 0 is there. Okay, 0 is there. We do not have problem with 0. So determinant of 0 matrix is 0. So we are okay with the 0. So let us do the addition part. So what we have is determinant of A. So let A and B to be. Meanwhile, others please keep thinking whether this is vector space or not, and vector subspace of M3R or not. A, B in M3R. So what does this mean? Determinant of A is 0 and determinant of B is 0. Now what I want to check is determinant of A plus B. Right? We want to check whether A plus B belongs to W or not. Right? So what is determinant of A plus determinant of B? Can somebody tell me what is determinant of A plus determinant of B? Oh, sorry, determinant of A plus B, determinant of this element A plus B. Is this determinant of A plus determinant of B? No, it is not, right? Yeah, exactly. As Hetvi said, determinant of A plus B is not equal to determinant of A plus determinant of B. Okay, so this is not actually. So let me give you a quick counter example or something like to understand that why this is not equal. So let us take A to be this matrix 1 0 0 0 0 0 0 0 0. What is determinant? So this belongs to W. Okay. Anybody has any doubt in here? Because determinant of A is 0 here. Okay. Right? And I can take B to be this matrix 0 0 0 0 1 0 0 0 1. And this also belongs to 0 because determinant of B is also 0, right? Because one row is entirely or one column is entirely 0. So determinant is 0. Any doubt? But what is A plus B? It is this matrix, right? And does this belongs to the W? No, right? Because determinant of A plus B now is 1, which clearly tells that A plus B doesn't belongs to W. Okay, so this is not a vector subspace because addition is not satisfied here. Scalar multiplication? Yeah. Uh, Bharat, I mean, you agree that it is not a vector space, or is there any doubt? Agreed. Okay, great. So, is there any doubt, Arijit? Is there a doubt, or you are clear that why it is not a vector subspace of M3R? Okay. Okay, so this is not a vector subspace. So sometimes, as we are, I mean, for in case of trace and everything, the addition property, I mean, this property of of trace, which we were using for it to be vector subspace, is not a very, I mean, this property is not satisfier, and this is where the entire problem occurs in case of determinant. So this set determinant of A is equal to 0 is not a vector subspace. And this is quite interesting, not interesting, but yeah, this is very simple example because in this case, the A plus B becomes identity, multiplicative identity of M3R, and it is not vector space, vector subspace in M3R. Okay. So let us do. So this is how. So we got the flavor of everything. Okay. So first thing to check is whether 0 is there or not, and then go for checking multiplication and scalar multiplication and addition, whether they belong to our W or not, or our W is closed under scalar multiplication and or addition or not. That's how we will do. That's the process of checking whether something is vector subspace or not. Okay, so we'll move to next question. If you have any doubt related to vector subspace or not, this is the time. I mean, you can always ask later on also, but you can ask right now because we are discussing that. Okay. So we will move further. Okay. So we'll go for our next question. So what we want to do is we want to, so span of a set, right? So span of some set S in V is linear combination of elements from S in V. Okay, and linear combination means we are taking scalars from the base field, and we are taking all possible linear combination, and that is the span of that set. Okay, so we want to check. The next question is related to. We will check whether the element, the given element, is in span of given set S or not. Okay, for given U and S. So let us all take this. So our U is element 2 comma minus 1 comma 1, and my S is this set 1 comma 0 comma 2 and minus 1 comma 1 comma 1 in R3. Okay, or not? Yeah, it is subset of R3. So we want to check whether uh not check U belongs to span of S or not. When we say that an element belongs to span of S or span of this element, it means that we want to find, what does this mean? That we want to check. So what does this means? That we want to check whether there exists a scalar A and B from R. I mean, this R3 is, we are taking vector space over R. So our scalars are coming from the set of real numbers R. So that's why if we want to check whether there exists some scalars a b from R such that this u, okay, so this u here is some a into 102 plus b into minus 1 1 1 or not. So we want to check the existence of these elements, the existence of these scalars a and b from R. Okay, so what does this mean? So let me write this explicitly. So consider this u is what? U is 2 minus 1 1, and we want to check whether a and b exist or not. So let us write this clearly: minus 1 1 and 1. Okay, so what does this mean? That uh, just simplifying everything, a comma 0 comma 2a plus minus b comma b comma b, and what does this give me? 2 comma minus 1 comma 1 is equal to a minus b. This is just 0, so b, and what this is 2a plus b, right? So let us just compare both the side, and what this gives me: a minus b is 2, b is minus 1, and 2a plus b is 1. Okay, so from this we arrived at this. So we want to check whether there exists AB such that they satisfy this set, this linear system or not. Okay, so from here we already have that B is equal to minus 1, right? Then from first equation, so let me write this 1, 2, 3. So this is from 2. So from 1 what we get? A is equal to 2 plus B. And what is B? 2 in 2 plus minus 1. And what is that? 1, right? So from this first two equation, I got A to be 1 and B to be minus 1. But whatever we have, it must satisfy this third equation as well. Okay, because we also want this third coordinate to be equal to 1 with respect to these scalars A and B. So we also want to check whether this A and B satisfy this equation 3 or not. So let us start with LHS of 3. LHS of this 3 is what? 2 of 1 plus minus 1. So what is it? 2 minus 1, and this is 1, and this is RHS of this equation 3. So this A and B which we have got, I mean the A is equal to 1 and B is equal to minus 1, satisfy the above system of linear equation. So the required coefficients are what? A is equal to 1 and B is equal to minus 1. So B is equal to minus 1. Yeah. So what does this give me? That U is in span of S. Okay. So that means that U here we had the vector U is in span of these two elements set S. Any doubt here? Like how we got this, or how is this happening? Any kind of doubt? Or why we check this third equation when we already have the values of A, E just by first two equations? No, right? No doubts. Okay. So let's take second, again one question with the span. So now our U is minus 1 to 1, and S is again similar as what we had, minus 1 1 1. in R3. So again, we will write them as a linear combination. So A and B, we want to check. So similar to what we did here. We will, so I'm not writing this. Okay, so we want to find AB in short. That U must be, so we want what? A into 1 comma 0 comma 2. We want to find A and B in R such that A plus B into minus 1 1 1 to be equal to minus 1 2 1. So what does this give me? A minus B. So let me write it to be precise. Okay. So minus B, B, B is equal to minus 1 2 1. And what will this give me? A minus B. B 2A plus B is equal to minus 1 2 1. Okay. So now what system we get? That A minus B to be minus 1. B again is 2 and 2A plus B is 1. So let me again write this 1, 2 and 3. So from 2 we have B is equal to 2, right? Then from 1 what we get? A minus B is equal to minus 1. So this will imply A is equal to minus B. Oh, sorry. Minus 1 plus B. So this will be minus 1 plus 2. So it is minus 1. Oh, oh. Is it correct? Any doubt? Yes, A is equal to 1. Minus 2 plus 2, or minus 1 plus 2, it will be 1. So now we got from 1 and 2, we got A is equal to 1 and B is equal to 2. Right? But we also want this A and B to satisfy the third equation as well. So what its third equation? LHS of 3, let me write, it is 2A plus 3B. Oh, sorry, not 2A plus 3B, 2A plus B, which is 2 into 1 plus 2. So what is this? 2 plus 2? It is 4. And which is not equal to RHS of 3. Okay. So the A and B we satisfy first two equation does not satisfy the third equation. So what does this mean? That there exists no A and B such that they satisfies all these three equations simultaneously. Okay, so what this means that there does not exist any A and B such that we get the linear combination of elements from S with those A and B to be equal to the U which we have here. So this gives us that the above U does not belongs to span of S. Okay. So any doubt here? So understand from these two example that even when we get the values of A and B from first equation or first two equation, we must check the third equation whether the ABs which we have obtained they satisfy the third equation or not. Because as we saw in this example, it might not satisfy. So if you are giving the exam for this course, then please in hurry you might just keep checking this third equation and you might end up getting the wrong answer. Please do not do that. If you have A and B from first two equation, please do check whether it satisfies the third equation or not. Okay. So in this second question, we got that U is not in span of S. So now we'll check for third example. So now we'll do this third example for matrices, 2 cross 2 matrices. So let U be this matrix, and SB these two matrices, these three matrices, 1 0 minus 1 0 in M3 M2R. Okay, so similarly we want to find, okay, we want A B C in R such that A into this matrix 1 0 minus 1 0, B into this matrix plus C into this matrix is equal to this or not. Okay, we want to check this. And so what we get from here, so I am not writing all the scalar multiplication matrices. So at the end we will get A plus B into 0 plus C. So A plus C. Here A is 0, B 1 and C 1, B plus C. Here A is minus A, B 0, C 0. So minus A. And the fourth coordinate, it is A 0, B 1 and C 0. So it is B. And what this is, it is 1 0 0 1, right? So from this what we get? A is equal to 0 and B is equal to, so let me write all the four equations. So we are comparing now component wise. So we get A plus C is equal to 1, B plus C is equal to 0, minus A is equal to 0. So minus A is equal to 0 implies A is equal to 0, B is equal to 1. Okay. So from this, what we get, so let me write 1, 2, third equation and this fourth equation. So we want to find the value of C now. We already have, yes, exactly. So what we said that from first two equation, if we take this equation, then we get C is equal to 1. And if I take this equation from 2, I get C is equal to minus 1. Okay. So for this A and B's which we got here, we get two different values of C as per the equations. So C is equal to 1 and C is equal to minus 1. So this is not possible, right? So U doesn't belongs to span of S. Okay? Because no uh, A, B, C exist in R such that they satisfy this equation system simultaneously. Okay, I mean they all must satisfy all the equations for given ABCs, but that is not happening here. For if, because from these equations we are clearly getting A is 0, B is 1, but when we try to find the values of C using A and B, we are getting two different values. So no solution for this system of equation, and which implies that we do not have any scalars from R such that their linear combination with S will give us the required matrix U here. Okay, so any doubt in this question? Yes, and Bharat, as you said, that C is equal to 1 from the first question, but again, we said that C will also be minus 1 from the second equation. So that's not possible. Okay. So that's why check all the equations. Even if you had got the third, I mean, as I was saying, you got A, you got B, you got C from first equation, but still we have not yet checked this equation 2 yet. So if we get C to be 1 from first equation, then what it should have got. So if we are going from what we have been doing in so far for earlier questions, so from 1, we will get that A to be 1. And if you want to check the LHS of 2, it will be B is what? 1 plus 1, which is 2, which is not equal to RHS of 2. Okay. So this is also the thing. So we must check all the equations, whether they satisfy the obtained ABCs or the scalars, whichever you are taking the variables to be. They must satisfy all the equations. So even if you are getting the values using less number of equation, please check the remaining equation whether they satisfy by the obtained values of scalars or not. Okay, so we'll go to next question, question 7. So this is kind of a bit uh, question which will give you a different flavor altogether. So the subsets of a vector space V, and we want to check whether the following statements are true or not. Okay, we want to check the whatever statements which we will be writing here are true or not. Okay, so first question, first statement is that if A is a proper subset of B, then span of A is proper subset of span of B. What is your guess? Is this statement true or not? That if what is this say that A proper subset of B implies span of A is proper subset of span of B. What is your guess? Oh, okay. Hitvi is saying that it is true. Anybody else has any different guess? In Arijit, Renuka, Ayushi, Anushka, B, Sakshi. Anyone has any different guess than what Hitvi is saying? Okay, so what does this mean? So let me ask you one thing. What they are saying that A and B are proper, A is a proper subset of B. We do not have any other information about A and B. And what they are saying is that if that span of A is proper subset of span of B. Okay, so let me give you this thing. So if I take A to be just, so we will talk about in R2. So over R, so R is our base field. So A is minus 1 comma 1, or just not even minus 1. We will just take 1 comma 1. Okay. So what is span of this A? Can somebody tell me? It is all the elements of this form, right? A comma A, such that A belongs to R, right? No, it is not saying it is just a subset. Okay. It is saying also it has to be a proper subset. When I say proper subset, you know what proper subset means. Yeah, as Hetvi said, it is of the form A into 1 comma 1 such that A in R, right? Perfect. No, Arjit, yeah, I was saying that when we say proper subset, what does that mean? That there must exist a element B from element from span of B such that that is not in span of A. We are not saying it is subset. Subset, yes, definitely it will be a subset, but we want to it to be a proper subset. Okay, now let me show you this B. If we take this B, 1 comma 1 and 2 comma 2. What is span of this B? Can somebody tell me what is span of B? Yes, but ultimately what that is giving me? A11 plus B22. Uh, can somebody tell me that what will be the span of this set? It will again be elements of this form, right? Because see, what this 2 comma 2 is, it is anyway 2 into 1 comma 1, which is anyway belongs to span of this element 1 comma 1. Oh, not this element. Span of 1 comma 1. Is there any doubt here? To understand that span of B in this case is again a scalar multiplication of this element. We are in real numbers, we are not in integers. Take a few minutes, and if there is any doubt, please write in the comment that you are not able to follow that how span of B is this set. Take a moment, think about it. And if you have understood, please also write that yes, you have understood. That why the span of B is again this set. Understood, right? So we can see here that A is but now proper subset of B, right? But span of A is exactly equal to span of B, right? So this statement which is given here is false. Okay. So if A is proper subset of B, then it does not imply that span of A will be proper subset of span of B, because as you know that this R2, just because we are used to this, that R2 is span of this 1 comma 0, 0 comma 1, right? This we are everyone aware of. But I can just add extra element, right, to this, and just 1 comma 1 or as many number of elements you want. Span of this is again the same thing. Okay. So, the, or let me just keep it here. So just because A is proper subset of some set B, the span of A need not be properly contained in span of B. Okay, the proper containment we need not have. Yes, definitely there are sets where it happens, because if I had taken A is equal to just 1 comma 0 and B is equal to this set 1 comma 0 comma 0 comma 1, that in that case it is proper subset. But in general this statement is completely not, matlab, it is not true. So next question is now we want to show that if span of A is equal to span of B, if and only if A is equal to B. Is this true? Can somebody tell me why this is true or why this is false, or what is your guess? Span of A is equal to span of B. Do we need to have A is equal to B to have span of A is equal to span of B? We just did some work. Yes, exactly. As Bharat said that no, we can just use above. So we have from above example itself that A proper subset of B also gives us, I mean, not this, but we know that span of A is equal to span of B, but we had A properly contained in B, right? In above from above example, span of A was equal to span of B, but yes, as you also said, it is not necessary. We can also have, like just in above example, A was proper subset of B, but the other way around was, I mean, the spans were not holding that condition. Okay. So the reverse implication, not the reverse implication, the forward implication itself failed here. Okay, the span of A is equal to B. We did not have is equal to B. Okay, so this statement is again false. Okay, you are getting the idea that how things are happening here. I hope. And if you have any doubt, please feel free to ask doubts in chat or unmute yourself and ask. Feel free. Okay. Third question: if span of some set A is V and we have a subset of B, then we want to check whether span of B is V or not. What is your guess in this case? That we are given, these are given conditions that span of A is span of B, and we want to check whether span of B is V or not. Okay. So what is your guess for this? That if span of A is equal to V, I mean the V means the entire vector space. Oh, the entire vector space. Span of A is the entire space, and now B is some bigger set than A, and we want to check whether span of B is now entire vector space or not. Any guess? Uh, okay. So the statement is true, but the argument you are giving is not correct. I mean, the what we had in first example, that A was proper subset of B and span of A was equal to span of B, was in very particular case. Okay, we were choosing examples such that that would happen, but that is not the case always. A is properly contained in B, then we can have, we might have cases where vector space is entirely contained in B. But one thing which Arijit, I guess Arijit or someone, just a second, who? Yeah, when we were discussing the first question of these true and false statements, what Arijit said was, if A is contained in B, then span of A is contained in span of B. Okay, this is always true. Okay, this you can understand that, or let me just explain you. So our claim is that this statement is true. Or so what we want to show is span of B is equal to V. So I'm taking the longer route to explain this just to get the whole, uh, like how the span and everything works. So clearly note that the span of B will be contained in V, right? This is clear because span will always be inside our vector space. Okay, so now let U be in V. Okay, And we want to show that this U is in span of B. So U is in V, right? But what we are given that span of A is equal to V, right? So this implies this U also is in span of A. But from this condition, we have this is contained in span of B. Anybody has doubt in this statement? The one I'm highlighting right now. Anybody has doubt why this is here? I will explain this right now that why this happens. If you have any doubt in this statement, the one which I have just highlighted, please let me know. I will explain this. Otherwise, I will assume that you know this and I will use this further in my explanation. If you do not know how this happens, then please let me know. I will explain it right now. Okay. No response, so I assume that this happened. Even if you don't know how this happens and you do not want to ask it right now, please carry out this simple exercise. You will get that span of A will be contained in span of B. Okay, so this implies U belongs to span of B, and so this will get what, that U in V implies U belongs to span of B. This implies V is contained in span of B. Okay, clear? So from this and this, we get that span of B is equal to the entire vector space. So this happens when our span is entire vector space. So if span of smaller set is entire subspace, then the span of bigger set will also be a span of will also span the entire vector space. That's what this statement is saying. Okay, understand this statement that if A is contained in B and if span of smaller set, that is A, is entire vector space, then the span of the bigger set, that is B, is again the entire vector space. Okay, this was the takeaway from this question. And let us go to next question, that is, if A is subspace of V, if and only if span of A is A. And this is a really good question. What is your guess? They are saying A is a subspace if and only if span of A is entire A. Span of A is equal to A. Just a guess, true or false. What is your guess? Just guess one thing and then I can move ahead and explain you whatever it is. And why it is and why it is not. No guesses? Okay. So we claim that this is true. Okay. So let us try to go with the first implication that if A is a subspace of V, then we will show that span of A is equal to A itself. Okay. So clearly note that now we want to show that let me write this to be complete. Okay, so clearly that A is contained in span of A. This always holds, right? Span of A is contained in span of A. Now we want to show the other way around. So let A And now let A belongs to span of A. We want to show that span of A is contained in A. So we will choose an element A from span of A, and now we will show that it belongs to element A. Okay. So A belongs to span of A means what? That A is of the form this A U1 plus, no, not like this. Let me take U. Let us take U in span of A. Then this U is A1 U1 plus AN UN, where these AIs are in our field, scalar field. AIs are scalars, and UI belong to A, right? So far it's clear. This is trivial, right? U is in span of A, then it is UI belong to A, and that's it. Then for then what? But we have this information as well that A is subspace of V. A is a subspace of V, and what that does that mean? That this A subspace of means it is A is not it is A is closed under scalar multiplication and addition, right? So these UIs are in A because U is in span of A, and these UIs are in A, right? But then this AN into AI into UI is again an element of A because A is a subspace and it is closed under scalar multiplication. Now, when we add these AI UIs finitely many times, I mean A1 U1 plus A2 U2 plus AN UN, then A is again closed under addition. So this implies what? U belongs to A, right? Because A is subspace. So what we got, that U belongs to span of A implies U belongs to A. So this implies what? That span of A contained in A, and then from this this A contained in span A, we get that A is equal to span of A. Any doubt here? Please ask. Any doubt? I will give you a few seconds to just no doubt, right? Okay. So the other implication we need to show, as this is if and only if condition, we need to show that if span of A is equal to A, then we want to show that, okay, let me write this. Span of A is equal to A implies A is subspace. This is what we need to show. So we want to show that A is subspace. So what do we need to show? That if we take two elements, so we want to show that it is closed under addition and it is closed under scalar multiplication, right? So if we take that, so let A comma B belongs to A, then what we want? Whether A plus B belongs to A or not. Okay, this is what we need to show if we want to show that A is subspace. But this is true, right? A plus B belongs where? A plus B belongs to span of A, right? Which is A from given condition. So this imply what? A plus B belongs to A. Any doubt here? This was very, not very trivial, but more or less trivial kind of thing, because we are taking A plus B, A comma B from A, and we wanted to show that whether we want to show or check whether A plus B belongs to A or not. But what is A plus B? A plus B is just span of elements from A, because A and B are from A. But we are given that span of A is A again. So we get that A plus B is in A. And similarly, if we take C a scalar and A an element from A, then C dot A will be what? This will again belong to span of A, and which is what? A again. So this implies C dot A belongs to A, and we get it is closed under addition, and from this we get it is closed under scalar multiplication. So what this gives me, that A is subspace of V, right? Doubt? This was comparatively easier than what we proved in first implication. We just wanted to see that this A plus B and this scalar multiplication which we are trying to prove here are actually just these are elements from the linear span of A, and that is nothing but A in this case as we are given. So that's why A is again a subspace of V. Okay, I hope that is clear. Okay. Any doubt? Okay. I assume there is no doubt, because if you understood the first one, then it means you will definitely understand the second part. Okay. So let us move to the next question. So we want to check which of the following statements again are true or not. Which of the following are true? So first one is, there exists distinct u comma v comma w in M2R. So M2R is 2 cross 2 matrices over R, such that span of u comma v plus w is equal to span of u plus v comma w. Okay. What is your guess? So first understand that they are saying that there exists. Okay, this need not happen for any given u plus v plus not u plus v, u comma v comma w, or this need not happen for any given u v w, but they are asking whether there exist such pairs of u v w such that the span of u comma v plus w is equal to span of u plus v comma w. So we just want to give the existence. It means that even if we give one example, one explicit examples, we are through. Okay, so can somebody give me 3 elements from M to R such that this hold? We want them to be equal. Okay, so let me give the examples. So we just want 3 elements such that their spans of these 2 sets must be equal, right? So let us take, so we will work smart now. Okay, so let me take this element, and this element. Can somebody give me what is span of u comma v plus w. What is your guess? And what is span of u plus v comma w? Okay, so span of u comma v plus w. So first understand that if I take u, so u is what? My 1000. And what is v plus w? It is this element 5000. Again, w is 3000. And what is u plus v? U plus v is 3000. Okay, and we are in R. Okay, so span of these elements and span of this element is just this set 1000 into A such that A in R, or for this also, because U directly we have this element and this element belongs to span of U, so we are through. In this case, oh, let me write this here, U plus V. From this W, if we multiply it by scalar 1 by 3, 3000, we end up getting this element, and once we have this element here, we get this set here. Okay, these three elements U, V, W are such that their spans are equal. Any doubt here? We just wanted to show the existence, and we have given the explicit examples using this U, V, and W such that their span of these two sets is equal. Okay. And this is not the only way to do this. You can always choose UVWs of your choice, given the condition that they must satisfy this span condition, which we are asked to show. Okay. Now, a few. Second one, again, we want to show that there exists distinct UVW in R3 such that span of U comma V is not equal to span of U comma W. Can somebody guess this? This one, you should be giving me at least one example or multiple examples if you want. We want three elements from R3 such that span of UV is not equal to span of UW. Any guess? Okay, so since you are in R3, we will start with the standard basis of R3. Okay, so now what is span of U comma V? It is A into 1 comma 0 comma 0 plus B into 0 comma 1 comma 0 such that A comma B is in R. And what this is A comma B comma 0 such that AB in R, right? And now we can take span of U comma W. What this is? It is A into 1 comma 0 comma 0 plus C 0 comma 0 comma 1 such that A comma C in R. This is equal to A comma 0 comma C such that A comma C in R. Okay. And these two spans and these two sets are non-equal, right? Span of U comma V is definitely not equal to span of U comma W, right? This is clear because here we can vary the second coordinate or second second coordinate, but here it is always fixed 0. And to be precise or to give an explicit example, the element 0 comma 0 comma 1 belongs here, but element 0 comma 0 comma 1 doesn't belong here. Similarly, just an element 0 comma 1 comma 0 belong here, but 0 comma 1 comma 0 doesn't belong here. So I'm just making it bit visual for you. Okay, so these sets are not equal at all. Okay, so move to next question. Third one, that does there exist distinct? So, yeah. So does there exist okay, NCT U V W in M2R? Okay. Now we are back to matrices. U V W X. Okay. Such that span of U comma V comma W is not equal to span of V comma W comma X. Okay. Can we find such UVWX? Okay, so using this hint from the second question, can you guess what this UVWX could be? If you can't, I know you can't write matrix, or you can, but you don't want to write matrix in the chat, that's okay. But at least write something so that we will understand that what you are talking about. Any UVWX guesses from M2R, the way we did for here? We chose the standard basis. Can we do the same thing here? What is the standard basis of M2R? It is 1000, 0100. Yes, yes, that kind of thing. What we will do is, yeah, as Hetvi suggested, we can choose such kind of element. V to be W to be 0010 and X to be 0001. Okay, now in that case, when we take span of UVW, then it is what, if I write directly, it is span of, this is UVW such that, oh, not W, it is C, such that A, B, C in R. And similarly, span of VWX would be, VWX means we are having 0 here, no, let me write like this, B, C, D, such that B, comma C, comma D in R. Okay, so it's quite clear that this is not equal, similar to what we had. So if I take element from there exists element here which does not belong there, and element here in span of UVW which does not belong to span of VWX, right? So here span of these elements is not equal. Any doubt in this? It is simple. just explicit examples which we are giving here. Now, the last question. So we are okay. We are out of. We have still 3 minutes. This is last question. So we will start. So last question again, the similar kind of. Does there exist distinct UVW in R3? Now we are back to R3 such that now this has two conditions, that span of U and W must not be equal to span of UVW, but span of U and V must be equal to span of U, V and W. Okay. So we now want to choose U, V and W such that they satisfy two conditions simultaneously. Can somebody give me these UVWs? Now, note that in this case, our normal basis, not the normal, I mean the usual basis won't work because we want this condition to satisfy. If we choose our UVW to be the usual basis, then this condition won't satisfy because if we choose UVW to be usual basis, then this will span one a comma b. The span of this will be a comma b comma 0, and span of this will be a comma 0 a comma b comma c. And this span is not equal. Okay, so we want to choose our our UVWs smartly here because we want the span of U and W not to be equal to span of UVW, but span of U and V must be equal to span of UVW. Any guesses? Okay, so a way to think through this is note that the second condition, okay, that UV, the span of UV must be equal to span of UVW. So whatever UV span, W also satisfy that thing, right? So what does mean? If we choose W in the span of U and V, then this would happen, right? If W is in span of V, then span of UV will be equal to span of UVW because this third element is anyway in the span of the first two. Yeah, I mean 0, 0, 0 would work, but yes, and I mean Hetvi gave these elements that she chose U to be 1, comma 0, comma 0, V to be 0, comma 1, comma 0, and W to be 0, comma 0, comma 0. Okay, and this definitely satisfies the given condition because see, the span of U and V, U and W is what? It is span of U itself because 0 belongs to span of U, and this is not equal to span of U comma V. Let me write them explicitly. Span of U comma W is this set A00 such that A in R. And what is span of UVW? It is A comma B comma 0 such that A comma B is in R. Okay, and so first condition is satisfied that the span of these two is not equal. Now the span of U comma V, now we check what is span of this. This is again A comma B comma 0 such that AB is in R, right? And this we know is equal to span of UVW. The first condition is satisfied and the second condition is satisfied. So the elements UVW which we chose here, I mean the what Hetvi gave us satisfy this condition. And just to get hold of this thing and just to have some idea or puzzle kind of thing, please try to solve these questions on your own, this last four, such that this is good exercise to get the counter examples or examples for what you will be giving in the exam, because in the exam you might ask such kind of question where you will have to choose whether span of such thing exists or not. And if you do the practice of getting used to such kind of thing, getting the explicit example to satisfy yourself that yeah, such thing happens or such thing does not happen, would definitely help you to write the exams if you are writing the exam for this course. Okay, any doubts? Anything which you did not understand from this session which we did, or anything which you would like to understand? Yes, yes, the notes of this lecture, yes, whatever I have written, it will be provided to you definitely. I will share this with the uh, NPTEL team, and yes, they will provide these notes to you. So you will get the notes of this, whatever I am given in this, like in this live section. Other than that, any doubts you had from the lecture or anything which you would like to discuss right now? Can you explain proper subset example? Yeah, sure. Proper subset example, which one first? This one or which one? The first one we did in the beginning of the class, that one? Which one? Could you, or this one? Are you talking about this example? Yes, the span one, but which span? The one which I'm highlighting right now, the proper subset, how this is equal? Is this what you are asking? Abhi, or you can unmute if you want and ask me directly. And if you think that language, okay, question 7, this one, Abhi, can you write please if you want to understand the question 7 one? This one, the first question of problem 7, I guess you are asking. So yeah, because this is about the proper subset example. Okay. So what they are saying that if A is a proper subset of B, then span of A is a proper subset of span of B. This is what you want to understand. So what they are saying that A is a proper subset, but the span need not be proper subset of itself. Proper subset means A proper subset of B means there exists some element B in B such that B does not belong to A. Okay. There exists, A and B are such that A is set like this and B is this bigger set. There are elements which are not in A. And what they are saying is that if I have A properly contained in B, B has more elements than A. Okay. But what they are saying that if A is proper, then we want to check whether span of A is properly contained in span of B or not. This is the question. This is what the question is asking. But that we are saying that it is not true. It is not always true, because we can have examples where this does not hold, because this explicit example where A is this 1 comma 1, here the span of A was this A 1 comma 1, but span of B is what? 1 comma 1 comma 2 comma 2, or instead as we had chosen 0 comma 0, we can very well choose 0 comma 0 here. And what span of B will be? It will again be A comma 1 comma 1, because multiplication of 0 will always give me 0, and adding 0 to any element, it will be of this form, right? Plus B 0 comma 0, such that A comma B in R. And what this is? A comma A, or let me write A 1 comma 1 plus 0 comma 0, right? Such that I mean, b into 0 is anything, it's vanish. And when I add this element, I will similarly simply get a 1 comma 1. And now these two spans are equal, right? These two spans are equal. They are equal. But a is properly contained. Sorry, a is properly contained in b. I mean, a is properly contained in b, but span of a is equal to span of b. Okay? Is it clear now? B. Understood. Okay, great. Any further doubt? If anyone has any doubt, please feel free to ask. Sure. Okay. No doubts? Okay, so since I guess there are no more doubts, we will end the session for today here, and we will meet next week at the same time, Saturday at 3 p.m. Okay. Thank you. See you all next week. Bye.